Hey everybody. So a while ago I made this video about a smoothed random voltage style modulator, and Harry May here commented, I really like the glider LFO shape from Ableton, but when I take a look at the JavaScript code, it totally freaks me out. Uh, so I was curious because I was surprised to hear that this device uses JavaScript. So I took a look at it and found some interesting stuff and want to make a kind of follow-up video going through that code. Um, so first we'll look at this glider shape. So this is what it looks like. It's really very similar to the smoothed out random voltage. Basically what it is it's just taking a stream of random values and then it's just smoothly interpolating or gliding from one to the next. So let's take a look at how they do that. So we'll open Edit in Max here. We'll open up the patch. And we have basically shape and waveform here. One important thing to know is that where this shape and waveform is evaluated, where right now we do have glider selected, what's flowing into that is a phasor signal. So just a ramp shape signal, okay? And then going in there, it has this init glider, and it seems to create an envelope or a window, you could often call it, with this Blackman shape, which actually, I don't exactly remember how they use this, so I'll have to look more closely. But if we then open this next patch, this is in Gen. So we have inside of a Gen patch here, we have two components. One, which is an exponent, which is going to basically just add some shaping to this phasor so we could make it exponential or logarithmic. We're actually just going to skip this for now because it's basically just another layer of transformation that's happening to the phasor before it's actually used to do exactly what we did in the other video, which is every time that this phasor resets itself, we get a new random value, and then we glide from what we had before to what we're going to. So the real magic is inside of this waveform gen patch, and here we have some gen expert code. So we're working inside of a code box, which means that we're using gen but instead in code, and this is functionally the same thing as gen patching. So if you've seen me do gen patching on this channel, sometimes I like to do it that way, particularly because I'm so used to max patching that gen patching comes very naturally. But sometimes people, including me, like to use gen code, and neither is better than the other. It's just whichever you prefer. And so basically this gen code box contains all of the waveforms for all of the LFOs that they have here in the in the LFO device. And now the question that I'm curious about is, where is this wavelet buffer used? I think it's actually in the stray. Yeah, so it's actually used in the one that's called stray, which is a different shape than the glider. So this is actually inaccurately named. It should say init stray. But let's talk about the glider, because that's the one that we're here to talk about. And we'll actually start way up at the top here. So in CodeBox, there's a few things that you have to understand. The first is that you can, just like a normal gen patch, you can have buffers, you can have history, you can have parameters. You can also have functions that you define that you can then call. So like other programming languages, we can basically define a sort of routine within the code or a block of code that we want to be able to reuse and define it as a function so that we don't have to write that code out every time. And in Gen Codebox, when we want to have a function, we always have to put the functions first. So at the very top of the Gen Codebox file, we have the functions. Then it has the buffer, which we don't care about because it's not used for a waveform that we're using. And then we have some histories. In history, I've talked about it in other videos, and I talked about it in the last one, is a way for us to be able to achieve feedback. It's also a way for us to be able to kind of, we could think of it as a way to store a single value across processing frames of the Gen Patcher. And if you're not totally clear on what I mean by that, many of the most recent videos I've made explain these concepts in a little bit more detail. So for the glider, we actually have 3 of these histories. So there's 3 values that we're keeping track of. So one is called old drive, one is B, and one is A. And this G, I think, just means glider. So it's just making it clear that these histories are being used by the glider waveform. So after that, we then have some code that's going to be used by all of the waveforms. So we have a phase, which is the signal at inlet 1, which is just the phasor that we already looked at. Then we have the type, so the wave type, which this could have been a param. In fact, I probably would have made it a param, but this person chose to just pass the wave type in to the second inlet. Then we have a rate, which I don't think is used in our case, so we don't care about it. And then this val is also not used in our case, so we're just going to ignore these two. They're used for some of the other waveforms. So just keeping in mind that we have a phase and we have a type, we then come into the section where we evaluate each of these different wave shapes. So depending upon what the type is, if it's 1, it does the cosine. If it's 2, it does the phasor. If it's 3, it does the inverse phasor, and so on. We're going to scroll all the way down to the section for glider. So basically, if the type is 8 when it comes into the patcher, because it actually seems like they add 1 here. If it's 8 when it comes into the patcher, so it becomes 9, we're going to use this glider type, and this code is going to be executed, and all this other code is going to be ignored because we have this stream of else-if statements here. Okay, so the first thing they do is they just reassign this phase to a different variable, which they call drive. So literally, we're just kind of renaming or just putting that value in another place. And then we have this thing here that says if drive if drive minus old drive, so this is our history, is less than 0, then GB, which is another one of our histories, is equal to GA, becomes equal to GA, right? Make GB equal to GA, and then update GA with a new random number between 0 and 1, right? Because the absolute value, which makes negative numbers positive, of noise, which gives us a negative number between the range of -1 to 1. So this is going to be a random number between 0 and 1. So random between 0 and 1. This is make the history GB to GA. And this is basically, this is the same as delta drive is less than 0, right? If you're used to seeing it in gen patching, if I have a phasor here, phasor 1, and then I take the delta, and then I say, is that delta less than 0? This is exactly the same as what we're seeing here. They're just doing it differently, and the way that they're doing that is they're basically saying after this has been evaluated, they set that G old drive history to drive, and then they subtract old drive from drive. So we could even do the same thing. We could say phasor 1, we could say old phase, history old phase, and then we can subtract the phase, the old phase from the phase, and say, is this less than 1? This is the same as using delta, right? So that means that delta is kind of clever. Like delta has a history inside of it, right? There's a delay in here because delta has to keep track of what the value was on the last gen processing frame. So delta is kind of an interesting object, which is a little bit of a composite of some other operations that we could do with other more sort of primitive components within gen. Like we could get by in gen without having delta because we could always roll our own delta with these more simple components. So that's all that is, right? It's basically saying if the change in the phasor is negative, then what does that mean? It means that this phasor is resetting itself. And I can demonstrate that to you like so over here in MSP land using the same exact I need a tilde here. Using the same patching, we're going to get a pulse every time that phasor resets. So, and by the way, this is the same as using what, right? So these are all just different ways of doing the same thing. Okay. So basically we are identifying the start of a new phasor phase. And like when there's a new phase, get a new random number. And we can actually put that here. And then we'll assign B to A. And what we'll be doing later on down here is we're going to basically interpolate or glide or crossfade, you could say, from B to A, right? So we could think about B as being like the last value, the last random value that we had, and A is the next random value that we are going to. And this bit of patching here is exactly the same as using mix. So there's a mix object in Gen, which we can instantiate in the code with just the mix function. But this is the same thing because basically we just take, we'll talk about what this sine drive is in a second, but just think of it as a ramp between 0 and 1 that directs the kind of interpolation or the fading from B to A. We just multiply the value of that ramp that is on the range of 0 to 1 by GA, and then we subtract that ramp value from 1 and multiply that by GB, which again is exactly the same as using mix. And we're going to actually re-implement this in a second in a way that I would do it myself, which is not better or worse, but I think maybe is a little bit more in line with the way that I tend to teach things, and so maybe it'll make sense to you if you tend to follow along with these videos. This section, which we skipped and we're now getting back to, is just shaping the phasor so that we get a nice smooth interpolation from one random value to the next. So in the last video, you probably remember that when we were fading from each random value to the next, at first when we were just using a straight linear phasor, we were getting this kind of pointy shape where we'd have these like points basically at each point where we would get to the new value. And we used the ease package. We used kind of a sigmoid shape from the ease package in order to smooth out those transitions. That's what this is doing here. And the way that it's doing that is actually super clever. And I'm going to go over to a graphing calculator to show you because I think that will be the easiest way to do it. We can start with just a quote unquote phasor, and we could do the can I do, yeah, there we go. So we can think of this as like a phasor, right? If we zoom in over here on the range of 0 to 1. And what we eventually want is sort of like an S shape, right? So instead of something that's just straight like this, we want something that goes kind of like this for a while and then up and then like that, which is an S shape. We often call it a sigmoid. And one way that we can do that is to take the hyperbolic tangent of x, and this is going to give it to us on the range of like approaching 1 to approaching -1. So if we then add 1 to this and multiply the whole thing by 0.5, then we can start to get it. This is still not exactly what we want, but you can see that the general shape is there. And this is one way that sometimes we do this in Max. But in the way that they're doing it in this particular device is they're using a sine wave. So if we take sine of x, it's going to look like this. And what I'm going to do is I'm going to multiply this by 2 pi. So if we now zoom in, we've got you can see we've got a sine wave that goes through its whole process on the range of 0 to 1. If I now subtract or even add to this this phase in radians, pi over 2. Pi over 2. Is that correct? Or did I want to subtract? Okay, subtract. Then what I get, you might have noticed, is this kind of S shape from -1 to 1. So now if I add 1 to this, and then I multiply the whole thing by 0.5, then I get a nice S shape, which is actually now in the range of 0 to 0.5. So I think I need to multiply by pi here. There we go. Now I'm getting a really nice sigmoid, just like what we wanted, from 0 to 1. And that's what's now, rather than using this red line as our interpolation from one randomly generated value to the next, we're using this blue line. And that is what they have here in this code. So 0.5 plus 0.5 times, so this is the part where we remap the range from -1 to 1 to 0 to 1. Fast sine, which is a way of computing a sine with less computational expense in Gen. Then using the drive, which is just our phase, times pi minus pi over 2. So that's exactly what we had in Desmos. And then the result is that really beautiful, gliding, kind of sine-like, but not periodic wave. Okay, so let's try, just for fun, to re-implement this. So I'm going to use this new gen.codebox tilde in Max, which is really handy. So now I'm in a Max patch, but I can just have a gen codebox that I can edit directly in my Max patch. And what's beautiful about that is I can now have a scope that I can actually see while I'm writing my code. Okay, so we have our phaser. And I'm going to copy this code. And I'm just going to put it in a comment so I can keep track of stuff. So the first thing that we're going to want to do is give ourselves a history. And I think that the only one that I really care about is going to be the last value. So this is what the Ableton code called GB, but I'm going to name things what I think is a little bit more descriptively. So this is going to be the last random value that we had. Then we'll define a phase, which is in 1. And then we're going to take the delta of that, and so we'll call this pulse, which is basically going to be the phase reset. And we'll call this phase delta of, a pulse is phase delta, the delta of phase is less than 0. And if I send that to the output, you can see we're now getting a nice pulse train. And then we can define a variable called next. And we can use latch here. So latch is a way to basically selectively update the value of a variable when some other condition is true. So if we say latch, latch the thing that we're going to use to set the value, which is going to be absolute value of some noise. In fact, let's break things out really clearly. So we'll say random is absolute value of noise, which is just a random value on the range of 0 to 1, random between 0 and 1. So this is the pulse on phase reset. So same as phaser to what? Okay. And so we'll latch random when pulse. So this basically says, this is the same as saying if pulse, next equals random. But what's nice about this is we don't have to define next outside. We could, there's other ways we could do this. We could use a history to be able to kind of store next as a variable and then have an if function that allows us to selectively update that. But this latch is really nice because it allows us to kind of define next and then, but only change its value when pulse is true. Because if we were to put this inside of a this block here, then in cases where pulse, like the next variable would be constrained to this block. It would not be accessible outside of it. So this is kind of handy. And now let's watch next. So you can see now we're getting the stepped random voltage source. And then we can do the same thing for last. So we can say, actually, before we update next, we want to say last is latch next pulse. So if pulse last equals next. And we want to make sure we do this before we do this, because what we're going to do is when there's a pulse, we'll say, oh, it's time to get a new random value. Let's set the old random value to be, let's set last to be equal to the old random value, and then let's set next to be equal to the new random value. And then let's just start with doing the kind of pointy version of the waveform. So we'll say glide is equal to mix, and we're going to mix from last to next over phase. And then we can monitor that. And we should, if I did it correctly, which it appears that I did not. Okay, let's try doing the other way. So history, next. And we'll get rid of all this. And then we'll just use if. So if pulse last is next, and next is random. And we can put the random in here too. Oh, how foolish. Next is equal to random. Okay, there we go. So now that should work. Okay, so now we're getting the pointy signal. And so now we just need to do the sine wave interpolation part. So we could just copy this. There's also another cool way to do it. I don't know whether it's faster or slower. I think fast sine's probably pretty good. But another way that we can do this is just use cycle, because cycle, whether in gen or in MSP, is actually a lookup of a sine wave that is already sitting in a buffer. So cycle you can actually think of as just being like a wavetable, basically. It's just a sample of a single cycle of a sine wave, actually a cosine wave, I think. And we just looked that up. So what we can do, and I'm gonna call this interp. Let's just start by taking cycle. We're going to use the phase, and then we're going to set this special attribute of cycle, which is called index, and we're going to set that to phase, because by default, this cycle object or cycle function takes a frequency. But in this case, we're going to pass a phase into it, which means that we're going to just drive this wavetable with a phasor. And I will send that to the second outlet so that we can see it. And there it is, a nice sine wave. And now if we take the phase times 0.5, right, because we did the cycle object, it generates a sine wave. Normally when we use sine in math, we need to use a input on radians on the range of 0 to 2 pi. But with cycle, we use a normalized input on the range of 0 to 1. So when we have drive here, drive times pi, right? Drive is on the range of 0 to 1. If we have drive times pi, it's like saying half of the cycle's range. So we'll say phase times 0.5, and let's just see what that gets us. So something like this. And now all we have to do is the phase reset, which I think is going, in our case, to be adding 0.5. I don't remember. Yes. So where we had a phasor before, and we can actually send the phasor to out 3. Now we get a nice sigmoid shape, which is on the range of -1 to 1. So we're going to fix that by adding 1. So now it's on the range of 0 to 2, and then multiplying 0.5. So now we have a nice sigmoid there, and then we're just going to replace the phase with interp inside of glide, and there it is. And this is on the range of 0 to 1, so we can update this scope. So we just recreated the same thing using different set of code. Hopefully that kind of helps you grasp what's going on here. Hopefully watching this helps you just make sense of this. Let me add some comments and then we'll be done with the video. So we're going to create a sigmoid shaped wave using the sine function. And this is output of a sine wave between negative pi over 2 and pi over 2. And I don't know why our latch thing didn't work. I'm sure I did something wrong, but I don't know. But this works just fine. So if there's a pulse, get a new next value and update last, right? And then we'll say interpolate from last to next using interp. All right, that's it. Hopefully that helps you learn a little bit of CodeBox and start to relate some of these concepts together across Gen and MSP and patching and CodeBox. Again, Graham mentions this all the time. CodeBox is no better than Gen. It's no more like the code is no more like performant or anything like that. It's just a different way to write the same thing. So if you're more comfortable with patching, then use patching. If you're more comfortable with code, then use code. It is nice to be able to read both because you will encounter both out in the wild. So you know, developing that faculty can be helpful because when we make stuff in Max, very often we're making things from examples that other people have already made. So being able to kind of adaptively reuse other people's work is one of the joys of being a Max programmer. All right, thanks so much. I'll see you next time. Bye-bye.